October 1943. The morning air over northern Germany hung heavy with the smell of spent cordite and aviation fuel. Oberleutnant Werner Schroer climbed into his Messerschmitt Bf 109 at Wunstorf airfield, the leather of his flight suit stiff with cold. Around him, 12 other fighters were preparing for takeoff, their engines coughing blue smoke into the autumn sky. Intelligence reports confirmed what every Luftwaffe pilot now dreaded. Another formation of American B-17 flying fortresses was crossing into German airspace, over 200 of them. Their target, the ball-bearing factories at Schweinfurt. Schroer had been flying combat missions for 18 months. He had 23 confirmed kills, most of them RAF bombers caught over the North Sea during night intercepts. But the Americans were different. They came in daylight, in formations so tight that their defensive firepower could shred a fighter in seconds. And they kept coming, week after week. More bombers than Germany could shoot down, more than Germany could replace. At altitude, the contrast between the two air forces became mathematical. The German fighters climbed through thin air with precision. Each aircraft was a masterpiece of engineering, built by skilled craftsmen who understood that every rivet mattered. Every weld was inspected, every tolerance calculated to the tenth of a millimeter. The Bf 109 that Schroer flew that morning had been assembled over 6 weeks in the Regensburg plant, each component fitted by hand, each system tested under pressure until it performed flawlessly. The armament alone represented months of development. One 20mm MG 151 cannon mounted in the engine, firing through the propeller hub. Two 13mm MG 131 machine guns synchronized above the cowling, and in the gun pods beneath each wing, additional 20mm cannons with 60 rounds each. The firepower was devastating. German engineers calculated that 15 to 20 hits from the MG 151 could bring down a heavy bomber. With the additional wing cannons, Schroer's fighter carried enough explosive shells to destroy 3 B-17s if his aim was perfect. But perfection, he had learned, did not win wars. Numbers did. At 12,000 meters, the bomber formation appeared on the horizon. From this distance, they looked like a swarm of insects, moving with mechanical coordination. Schroer counted 4 combat boxes, each containing 21 bombers stacked in defensive layers. The Americans called it mutual protection, the Germans called it a flying fortress, and the name fit. Every B-17 carried 11 50-caliber machine guns. In a tight formation, those weapons created overlapping fields of fire that could track a fighter through any attack approach. Schroer's squadron leader gave the order over the radio. Head on, attack, 3 o'clock high, dive through the formation, fire at 400 meters, break away at 100. It was the only tactic that worked. From the front, the B-17's defenses were weakest. Only 2 machine guns in the nose could return fire during a head-on pass, but the window of opportunity lasted only seconds. At closing speeds exceeding 800 km per hour, a pilot had less than 2 seconds to aim, fire, and pull away before colliding with 30 tons of American bomber. Schroer rolled inverted and dove. His wingman followed. Behind them, 11 other Bf 109s dropped through the sky like stooping falcons. The bomber formation grew larger in his gun sight. He could see the nose art on the lead aircraft, a cartoon figure painted in bright colors. Below it, the bombardier crouched behind his Norden sight, calculating the release point. Schroer selected his target, a B-17 in the second rank, slightly offset from the formation. Its position made it vulnerable, easier to hit without crossing, through the defensive fire of other bombers. 400 meters. He pressed the trigger. The Bf 109 shuddered as all 5 weapons fired simultaneously. The 20mm shells traced bright arcs through the air. Schroer watched them converge on the bomber's nose section. Glass shattered, metal tore. He counted 7 hits, maybe 8. The nose cone disintegrated, the B-17's cockpit filled with smoke, but the bomber did not fall. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Schroer pulled back hard on the stick, the G forces crushing him into his seat as the Bf-109 clawed upward, missing the bomber by less than 10 meters. He rolled right, scanning for his wingman. The fighter was gone. In its place, a streak of burning fuel marked where 30mm rounds from another bomber had found their target. He climbed back to attack altitude and looked for the damaged B-17. It was still there, still flying, still holding formation. The entire nose section was destroyed. The Bombardier's station blown open to the freezing wind. But the aircraft continued toward Schweinfurt, its engines running smoothly, its bomb bay doors preparing to open. Schroer had put 8 20mm explosive shells into that bomber. 8 hits that should have torn through aluminum like paper. 8 hits that should have ignited fuel lines and hydraulic systems. 8 hits that should have sent the aircraft spiraling into the German countryside in flames. Instead, it flew on. He repositioned for another attack, this time from the rear quarter, where the tail gunner had only limited traverse. He closed to 300 meters and fired again. The MG-151 cannon hammered, 30 rounds. He watched the tracers walk across the bomber's right wing, stitching a line of explosions from wingtip to fuselage. The wing fuel tanks should have erupted. Every German aircraft carried bladder tanks filled with fuel, protected only by thin aluminum skin. A single explosive shell in those tanks created an instant fireball. The B-17's wing erupted with hits. Metal fragments spun away in the slipstream. Holes the size of dinner plates appeared in the wing surface. Schroer counted 14 direct impacts on the fuel tank area. He expected flames. He expected the wing to separate. He expected the bomber to die. It did not. The bomber continued flying. No flames. No fuel streaming from punctured tanks. The wing remained attached. The engines kept turning. Behind his oxygen mask, Schroer felt something close to disbelief. It violated everything he understood about aerial combat. A fuel tank hit by explosive ammunition did not survive, could not survive. The physics were absolute. The chemistry was inevitable. Fuel plus fire equaled destruction. But the Americans had changed the equation. Schroer made 3 more, attack runs. Each time, he achieved hits. Each time, the bomber absorbed punishment that should have been fatal. After the 5th pass, his ammunition counter showed empty. 60 rounds from the wing cannons, 200 rounds from the engine-mounted gun, 300 total shells fired at a single target. The textbooks said 15 to 20 hits could destroy a B-17. Schroer had scored at least 47. The bomber was still flying. Out of ammunition and low on fuel, Schroer turned for home. Behind him, the American formation continued toward Schweinfurt. Around him, other German fighters were breaking off, their ammunition expended, their fuel gauges dropping toward empty. The sky was filled with parachutes. Some were German, most were American. But for every B-17 that fell, 10 more pressed on toward the target. At Wunstorf, Schroer landed with his warning lights flashing. The ground crew swarmed his aircraft, counting the hits it had taken during the battle. 18 bullet holes, 3 from .50 caliber rounds that had punched through the tail section. Schroer climbed out of the cockpit and stood on the wing, watching the mechanics examine the damage. His hands were shaking, not from fear, from the realization of what he had witnessed. The crew chief approached. "How many did you get?" "None," Schroer said. "I hit one bomber 47 times. It kept flying." The crew chief looked skeptical. 47 hits? I counted every one. Nose, cockpit, wing tanks, engines, everything. It should have gone down 5 times over. The wings caught fire? No fire. The fuel tanks took direct hits. No flames. The crew chief was silent for a moment. Then he said something that would echo through Schroer's memory for the rest of the war. "They've built something we can't break." That evening, in the pilot's ready room, Schroer filed his after-action report. The intelligence officer recorded his account with growing concern. Multiple, explosive hits on fuel tanks with no resulting fire. 40-plus rounds expended on a single target without achieving a kill. The mathematics didn't work. The reports from other pilots told similar stories. Bombers taking catastrophic damage but continuing to fly. Fuel tanks riddled with holes that refused to leak. The intelligence officer made a notation at the bottom of the report. Suspected new fuel tank technology. Request technical assessment. 2 weeks later, German engineers examined the wreckage of several B-17s that had crashed near Kassel. Among the debris, they found intact sections of wing structure. Inside those wings, they discovered something that changed their understanding of what they were fighting against. The fuel tanks were not simple aluminum cells. They were composite structures made from layers of rubber, fabric, and synthetic materials that no German aircraft possessed. The outer layer was vulcanized rubber, impervious to fuel. The inner layer was untreated natural rubber that swelled when it contacted gasoline. Between them, a matrix of reinforcing fabric provided structural integrity. When a bullet or shell fragment penetrated the tank, fuel would seep into the rubber layers. The untreated rubber absorbed the fuel and expanded, swelling to fill the puncture. The process took approximately 12 seconds from perforation to seal. A captured American technical manual described it in clinical terms: self-sealing fuel tanks, effective against 50 caliber armor-piercing rounds and 20 mm high-explosive shells. Sealing time, 10 to 15 seconds. Weight penalty, 42 kilograms per tank. Fuel capacity reduction, 18%. For the German engineers studying that manual, the numbers represented more than technical specifications. They represented a philosophical difference in how the two nations approached warfare. Germany, built for quality, each aircraft was optimized for performance, stripped of unnecessary weight, refined until it achieved maximum speed and maneuverability. Adding 42 kilograms of rubber to protect fuel tanks was unacceptable. It reduced range. It decreased climb rate. It compromised the precision that German engineering celebrated. America built for survival. The self-sealing tanks made B-17s slower and heavier. They carried less fuel and fewer bombs. But they brought their crews home. And they could be manufactured in quantities that Germany could never match. Every B-17 that rolled off the production line in Seattle carried self-sealing tanks as standard equipment. The rubber compounds were mass-produced by tire companies. The installation process was standardized, repeatable, immune to variations in craftsmanship. The German report concluded with a statement that acknowledged what Schroer had learned in the sky over Schweinfurt. The American advantage does not lie in superior technology. It lies in their ability to accept imperfection in pursuit of numbers. Their bombers are slower, less maneuverable, and carry smaller bomb loads than optimal designs. But they survive. And because they survive, they return. And because they return, they multiply faster than we can destroy them. Werner Schroer flew 43 more combat missions before the war ended. He shot down 17 aircraft, bringing his total to 40 confirmed kills. But he never forgot that October morning over Schweinfurt, the morning he fired 300 rounds at a single bomber and watched it fly away, the morning he learned that wars were not won by the best machines. They were won by the machines that kept working when everything else failed. In January 1944, Schroer encountered another B-17 formation over Berlin. This time, he chose his attack carefully. He studied the bomber formation, looking for signs of damage or weakness. He found one. A B-17 lagging behind the main formation, its number 3, engine trailing black smoke. The aircraft was wounded, vulnerable, an easy kill. Schroer positioned his Bf 109 for a beam attack, approaching from the side where the bomber's defensive fire would be weakest. He closed to firing range and pressed the trigger. The 20mm cannon shells walked across the bomber's fuselage, concentrating on the wing route where the fuel tanks were located. He counted 23 direct hits. Every one struck the wing fuel tank area. Every one should have been fatal. The bomber kept flying. No flames, no fuel streaming from the wing. Just small puffs of torn metal where the explosive shells had detonated against the self-sealing tanks. Schroer watched through his gun sight as the rubber layers inside those tanks began their work. 12 seconds. That's all it took. 12 seconds for the untreated rubber to swell and seal the punctures. 12 seconds that transformed lethal damage into a minor inconvenience. He broke away from the tack and climbed back to altitude. Around him, the sky was filled with German fighters, all firing, all scoring hits, all watching as the American bombers absorbed punishment that should have been catastrophic. For every B-17 that fell, dozens more continued toward their targets. The production factories in America were building them faster than Germany could shoot them down. The mathematics were brutal. America produced 15,000 B-17s during the war. Germany destroyed approximately 4,700. The difference, 11,300 bombers, represented 11,300 examples of American industrial philosophy. Build them strong enough to survive, build them simple enough to repair, build them fast enough to overwhelm. The self-sealing tanks were not the only innovation that kept B-17s flying. Armor plating protected the crew. Redundant control systems allowed pilots to fly with massive damage. The aircraft's structure was designed to absorb battle damage and maintain flight, but the fuel tanks represented something more fundamental. They represented acceptance that aircraft would be hit, that crews would be wounded, that missions would be costly. German aircraft doctrine rejected that acceptance. The Luftwaffe designed for air superiority, for dominance through superior performance. German fighters were faster, more maneuverable, more heavily armed. But they were also more fragile. A single, well-placed round could ignite a fuel tank. A minor control system failure could force an abort. The pursuit of perfection had created aircraft that performed brilliantly in ideal conditions, but struggled to survive the chaos of sustained combat. America designed for attrition. The B-17 was built to be damaged and keep flying, to lose engines and maintain altitude, to take hits that would destroy lesser aircraft and bring its crew home. The self-sealing tanks embodied that philosophy. They did not prevent damage. They managed it. They turned catastrophic failures into survivable wounds. In February 1944, a B-17 named All-American returned to base in North Africa with its rear fuselage nearly severed after a mid-air collision with a German fighter. The tail section hung by a few structural members and control cables. The crew could see clear through the aircraft from cockpit to tail. But the bomber flew. Its fuel tanks, despite being punctured by fragments from the collision, had sealed themselves. No fire, no fuel loss, just rubber doing what rubber does when it contacts gasoline. Swelling, expanding, sealing. The German fighter that collided with All-American disintegrated on impact. Its fuel tanks exploded. The pilot was killed instantly. Two different philosophies of aircraft design meeting in a violent collision that demonstrated which approach would survive the war. By late 1944, Luftwaffe intelligence had compiled extensive documentation on American self-sealing technology. They understood the chemistry. They understood the mechanics. Several captured B-17s had been thoroughly examined, their fuel tank systems disassembled and analyzed. German chemists developed their own versions of self-sealing compounds. Prototypes were built. Tests were conducted. The results were technically successful. The German self-sealing tanks worked as well as the American versions. But they arrived too late. By 1944, Germany's synthetic rubber industry was collapsing under Allied bombing. The factories that could produce the specialized compounds were being destroyed. The chemical plants that synthesized the base materials were running at 20% capacity. Even if the rubber had been available, there was no capacity to retrofit existing aircraft. The Luftwaffe was struggling to produce enough fighters to replace combat losses. Modifying production lines to install self-sealing tanks would reduce output at a time when quantity mattered more than quality. The decision was made to continue building fighters without fuel tank protection, accepting that they would burn more easily, accepting that pilot casualties would be higher, accepting that the war was already lost. Werner Schroer survived the war. In 1947, he attended an aviation technology exhibition in London. Among the displays was a cutaway section of a B-17 wing showing the internal structure and fuel tank system. He stood in front of that display for nearly an hour, studying the layers of rubber and fabric that had kept so many bombers flying despite his best efforts to shoot them down. A British aviation engineer noticed his interest and struck up a conversation. Schroer explained his background, his combat experience, his encounter with the B-17 over Schweinfurt. The engineer listened quietly, then asked a simple question. "How many times did you hit that bomber?" 47 times. I counted every round. The engineer pointed at the fuel tank display. See these layers? Each one is designed to absorb and contain a specific type of damage. The outer vulcanized rubber resists fuel penetration. The middle untreated rubber swells on contact with fuel. The inner fabric provides structural support. When your shells hit this tank, they created perforations, but within 12 seconds, those perforations sealed themselves. The bomber could have taken 200 hits on its fuel tanks and still flown home. Schroer stared at the display. We never had anything like this. No. You didn't, and that's why you lost. The statement was blunt, perhaps cruel, but it was accurate. Germany had lost the technological race not because its engineers lacked skill, but because they lacked the industrial capacity to implement their innovations at scale. Self-sealing tanks required rubber. Rubber required chemicals. Chemicals required functioning, factories. Factories required protection from bombing. Protection required air superiority. Air superiority required fighters. Fighters required fuel. Fuel required refineries. Refineries required bombing protection. The cycle was vicious and unsustainable. By 1944, Germany was cannibalizing itself, stripping resources from one critical system to temporarily sustain another. The Luftwaffe was flying fighters without adequate fuel, using pilots without adequate training, defending factories that could no longer produce adequate materials. America faced no such constraints. Its factories operated at full capacity, protected by oceans from enemy bombers. Its rubber industry produced millions of tons of synthetic compounds. Its oil refineries ran continuously, supplying fuel for training and combat. The self-sealing tanks on B-17s represented just one small piece of a massive industrial machine that could outproduce, outsupply, and outlast any opponent. The comparison was mathematical. In 1943, America produced 85,000 aircraft. Germany produced 25,000. The American aircraft carried self-sealing tanks, armor plating, and redundant systems. The German aircraft were lighter, faster, and more vulnerable. By 1945, the numbers had diverged even further. America produced 96,000 aircraft. Germany produced 7,000. For Werner Schroer, standing in that London exhibition hall, the self-sealing fuel tank display represented more than just a technical innovation. It represented the fundamental difference between two nations at war, one built for perfection, the other built for survival. Perfection could not win a war of attrition. Survival could. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. In 1943, the United States Navy published a technical report titled The Development of Self-Sealing Fuel Tanks. The document described the testing process that validated the technology. Navy engineers at Dahlgren Proving Ground had suspended sample tanks from frames and fired at them with various weapons, 30 caliber rounds, 50 caliber armor-piercing, 20 mm explosive shells. The results were documented with scientific precision. A 30 caliber bullet created a puncture that sealed in 8 seconds. A 50 caliber armor-piercing round created a larger hole that sealed in 14 seconds. A 20 mm explosive shell created multiple perforations that sealed in 18 to 22 seconds. The report concluded that self-sealing tanks provided effective protection against all standard aerial weapons used in 1943. German intelligence obtained a copy of that report in early 1944. It was translated, analyzed, and distributed to Luftwaffe technical units. The document confirmed what German pilots had been reporting from combat. The American bombers could absorb extraordinary amounts of battle damage and continue flying. The self-sealing tanks were a significant factor in that survivability. But understanding the technology and implementing it were different challenges. The report specified the materials required for tank construction. Vulcanized rubber compounds meeting specific hardness and elasticity standards. Untreated natural rubber with controlled swelling characteristics, reinforcing fabric with defined tensile strength. Adhesives capable of bonding rubber to aluminum under temperature extremes from -40 to +70 degrees Celsius. Each material had to be manufactured to exact specifications. The vulcanized rubber required precision molding. The natural rubber required careful quality control to ensure consistent swelling rates. The fabric required specific weaving patterns. The adhesives required chemical formulation beyond standard, industrial capability. For American manufacturers in 1943, these requirements were challenging but manageable. Goodyear, Firestone, and U.S. Rubber had the industrial capacity and technical expertise to produce the components at scale. Thousands of workers in factories across the Midwest manufactured millions of self-sealing tanks. The production process was standardized, documented, and replicated across multiple facilities. For Germany in 1944, the same requirements were impossible. The synthetic rubber industry was operating at minimal capacity. The natural rubber supply had been cut off when Japan lost control of Southeast Asian plantations. The chemical industry was prioritizing explosives and synthetic fuel. The fabric industry was producing parachutes and uniforms. There was no spare capacity for a complex new technology that would require months to implement and reduce fighter production during the implementation phase. The decision was pragmatic but fatal. Continue building fighters without self-sealing tanks, accept higher pilot casualties, hope that training and tactics could compensate for inferior survivability. The arithmetic did not support that hope. German fighter pilot losses in 1944 exceeded replacement rates by 40%. For every 4 pilots killed, only 2.5 new pilots completed training. The shortfall grew exponentially. By early 1945, Luftwaffe squadrons were operating at 60% strength with pilots who had less than 50 hours of combat experience. American bomber crews, protected by self-sealing tanks and other survivability features, were completing tour lengths that German planners considered impossible. 25 missions. 35 missions. Some crews flew 50 missions and returned home. The self-sealing tanks did not guarantee survival. They increased the probability of survival just enough to matter over hundreds of missions, thousands of aircraft. Werner Schroer calculated the statistics after the war. During his 43 combat missions, he engaged with approximately 200 American bombers. He scored confirmed hits on at least 60 of them. Of those 60, he achieved kills on 17. The remaining 43 bombers survived, despite taking damage that should have been fatal. That survival rate, 71%, was consistent across all Luftwaffe fighter units engaging B-17s. The implication was clear. Without self-sealing tanks, the survival rate would have been significantly lower, perhaps 30%, perhaps 20%. The additional 50% survival probability, multiplied across thousands of combat missions, meant the difference between a sustainable bombing campaign and an unsustainable one. In October 1943, after the first Schweinfurt raid, the 8th Air Force lost 60 B-17s out of 291 attackers, a 20% loss, rate that was unsustainable. The bombing campaign was suspended for 5 months while the Air Force developed long-range escort fighters. When the campaign resumed in early 1944, loss rates dropped to 6%. Part of that reduction came from fighter escort, part came from improved tactics. But a significant portion came from survivability features like self-sealing tanks that allowed damaged bombers to continue flying when earlier aircraft would have fallen. The German response to that improved survivability was to develop heavier weapons, 30mm cannons that could destroy a bomber with 3 hits, rocket projectiles that could engage formations from beyond defensive gun range. Air-to-air bombs dropped from above onto tight formation boxes, but heavier weapons meant fewer rounds. Rocket projectiles were inaccurate. Air-to-air bombs rarely hit. The technological arms race favored the side with industrial capacity to implement proven solutions at scale. America had that capacity. Germany did not. By mid-1944, the outcome was inevitable. German fighters, flying with inadequate fuel, piloted by undertrained crews, armed with weapons they carried insufficient ammunition for, faced a bombing campaign that arrived daily with overwhelming force. The self-sealing fuel tanks on those bombers were just one small factor in a vast equation, but they mattered. Every bomber that survived because its fuel tanks sealed meant one more successful mission, one more factory destroyed, one more step closer to Germany's industrial collapse. Werner Schroer wrote in his memoir, published in 1962, "I fought the war in the air believing that skill and courage would determine the outcome. I was wrong. The outcome was determined in factories I never saw, by workers I never met, using technologies I never understood until it was too late. The Americans won because they built systems that forgave mistakes and absorbed damage. We lost because we built systems that demanded perfection and broke under pressure." That assessment, written 17 years after the war ended, captured the essential truth. Self-sealing fuel tanks did not win the air war over Europe, but they represented the philosophy that did. Accept imperfection. Build in quantities that overwhelm the enemy's capacity to respond. The B-17 was not the best bomber of World War II. It was the bomber that could take punishment and keep flying, that could be mass-produced and maintained by moderately skilled personnel, that could complete its mission even when damaged. The self-sealing fuel tank embodied all those principles. It was not perfect. It added weight. It reduced fuel capacity. It required specialized materials and complex manufacturing, but it worked. And because it worked, bombers came home. And because bombers came home, crews survived to fly again. And because crews survived, the bombing campaign continued. And because the campaign continued, Germany's industrial capacity collapsed. In a war decided by industrial mathematics, the side that could protect its workers and multiply its resources would always defeat the side that demanded perfection from exhausted factories. The self-sealing tank was not revolutionary technology. British aircraft had used similar systems since 1940. Japan's aircraft lacked them entirely, leading to catastrophic losses in the Pacific. Germany understood the technology but could not implement it at scale. The difference between understanding and implementation defined the war's outcome. Germany understood how to build jet fighters, but lacked the materials and fuel to deploy them effectively. Germany understood how to build V-2 rockets, but those rockets achieved nothing strategic. Germany understood how to develop advanced radar and fire control systems, but could not produce them in sufficient quantities to matter. America understood that wars were won by adequate solutions deployed at overwhelming scale. The self-sealing fuel tank was adequate. It did not eliminate fuel tank fires. It reduced them. That reduction, multiplied across 15,000 B-17s and tens of thousands of missions, saved thousands of lives and enabled a strategic bombing campaign that destroyed Germany's ability to wage industrial warfare. For Werner Schroer, the lesson came too late to matter. By the time he understood what he was fighting against, the outcome was decided. But the lesson remained relevant. In warfare, adequacy multiplied by quantity defeats perfection multiplied by scarcity. Simple systems deployed at scale defeat complex systems deployed in limited numbers. Survival matters more than performance when survival allows you to return and fight again tomorrow. The self-sealing fuel tank was simple. Layers of rubber that swelled when they contacted fuel. No moving parts, no electronics, no complexity beyond careful material, selection and quality control. But that simplicity was its strength. It could be manufactured by tire companies. It could be installed by aircraft workers with minimal training. It could survive battle damage and continue functioning. It could be maintained in forward bases with basic tools and supplies. German fuel tanks were lighter, more efficient, and more sophisticated in their engineering, but they were also fragile. A single explosive shell transformed them into fireballs. There was no second chance. No opportunity to return home, no possibility of repair. The pursuit of engineering excellence had created a vulnerable system that could not survive the reality of sustained aerial combat. America's fuel tanks were heavier, less efficient, and cruder in their engineering. But they survived, and survival, in a war of attrition, was the only metric that mattered. The winter of 1944 brought Werner Schroer face to face with the consequences of technological inferiority. On a frozen morning in December, his squadron was scrambled to intercept yet another American formation. Over 300 B-17s and B-24s, escorted by P-51 Mustangs that could now follow the bombers all the way to their targets and back. Schroer's Bf 109 was showing the strain of continuous combat. The engine had been rebuilt twice. The airframe had been patched with salvaged parts from destroyed fighters. The cannon ammunition was a mixture of shells from 3 different production batches, each with slightly different ballistic characteristics that affected accuracy. There was no time for proper maintenance. No spare parts for non-critical systems. No replacement aircraft waiting in reserve. He climbed to intercept altitude and watched the American formation approach. The bombers flew in perfect boxes, their contrails writing straight lines across the winter sky. Schroer had learned to recognize the signs of experienced crews. Tight, formation spacing, coordinated evasive maneuvers, disciplined fire control that conserved ammunition for genuine threats rather than wasting rounds on distant targets. These were veteran crews flying veteran aircraft. Some of those B-17s had completed 20 missions, 30 missions. Their aluminum skins were patched with repair plates where battle damage had been fixed. Their engines had been swapped and rebuilt. Their fuel tanks had sealed themselves dozens of times, each puncture adding another small scar to the rubber layers that kept them flying. The American escort fighters arrived first, P-51s with drop tanks that extended their range beyond anything Germany could match. They came down through the bomber formation like wolves, hunting for German fighters before they could reach the bombers. Schroer's squadron scattered. 3 Bf-109s were shot down in the first minute of combat. The survivors tried to push through to the bombers, but the Mustangs stayed, with them, forcing turning fights that burned fuel and prevented attack runs. By the time Schroer broke free from a P-51 and positioned for a bomber attack, his fuel gauge showed 15 minutes remaining, not enough time for multiple passes, barely enough time to reach home base. He selected a bomber that had dropped slightly behind the formation, its number 2 engine feathered and windmilling silently, a damaged aircraft, vulnerable. He closed to 400 meters and fired. The 20mm shells converged on the bomber's left wing. He counted 12 hits, direct impacts on the inboard fuel tank. The wing erupted with small explosions as the shells detonated. For a moment, Schroer thought he had achieved a kill. The wing appeared to be coming apart, metal fragments spinning away in the slipstream, but there were no flames. The fuel tanks sealed themselves. 12 seconds. The bomber continued flying on 3 engines, slowly losing altitude but maintaining enough speed to stay with the formation. Schroer's ammunition counter showed empty. He turned for home, his engine sputtering as the fuel supply dropped toward zero. Behind him, the American bombers continued toward their target. Ahead of him, his airfield was under attack by another wave of bombers that had struck while his squadron was airborne. He landed at an auxiliary field 20 kilometers from Wunstorf. The runway was a hastily cleared strip of frozen ground. There were no hangars, no repair facilities, just a fuel truck and a handful of mechanics working in the open air. Schroer climbed out of his fighter and watched as the mechanics began counting damage. 23 bullet holes, 1 hydraulic line severed, oil pressure dropping. The aircraft would need 2 days of repair before it could fly again. 2 days Germany did not have. The next morning, Schroer was assigned a different fighter. A Bf-109 pulled from training duties and pressed into combat service. The aircraft was older, slower, and armed with only the engine-mounted cannon. No wing pods, no extra ammunition, just enough firepower to perhaps damage a bomber if every shot connected perfectly. He flew 3 missions in that aircraft before it was destroyed on the ground during an American strafing attack. His next fighter was even older. An early model Bf 109 with a less powerful engine and limited ammunition capacity. By February 1945, Schroer was flying whichever aircraft happened to be available, often taking off in fighters that should have been grounded for maintenance, burning fuel that was increasingly contaminated with impurities from desperate refining processes. The American bombers, meanwhile, continued their campaign with industrial precision. Each B-17 that survived a mission was repaired, refueled, and sent out again. The self-sealing tanks were inspected after every flight. Technicians checked for punctures, confirmed that the rubber layers had sealed properly, and certified the tanks for continued use. Minor damage was repaired. Major damage resulted in tank replacement. The entire process took hours, not days. Standardized procedures. Interchangeable parts. No heroic efforts required. German aircraft maintenance had become a desperate improvisation. Mechanics cannibalized, destroyed fighters to keep operational aircraft flying. Parts from different production batches were mixed and matched. Non-standard repairs were accepted as routine. Aircraft flew with systems that barely functioned, held together by ingenuity and determination, but lacking the industrial support that American maintenance crews took for granted. The comparison extended beyond fuel tanks. American bombers carried armor plating that protected crew positions. German fighters sacrificed armor for speed and maneuverability. American bombers had redundant control systems that allowed pilots to fly with significant damage. German fighters had single-point failures that could disable the aircraft with one well-placed round. American bombers could operate from rough forward airfields with minimal support equipment. German fighters required smooth runways and extensive ground infrastructure. Every design choice reflected a different philosophy. America designed for the reality of industrial warfare. Germany designed for an idealized vision of air combat, where skill and technology would overcome numerical inferiority. That vision had been wrong. By early 1945, it was catastrophically wrong. Werner Schroer's last combat mission came on March 28, 1945. He took off at dawn in a Bf 109 that had been rebuilt from 2 crashed aircraft. The engine was from one fighter, the wings from another. The armament was a single 20mm cannon with 40 rounds, not enough ammunition for a sustained engagement. Barely enough for one attack pass. The mission briefing was simple: intercept American bombers attacking Berlin, disrupt the formation, prevent accurate bombing. The intelligence officer did not mention that there were over 1,200 American bombers in the attacking force, or that they were escorted by 400 fighters, or that German fuel reserves were so low that this might be the last major defensive operation the Luftwaffe could mount. Schroer climbed through heavy clouds and emerged at altitude to see the largest aerial formation he had ever encountered. The sky was filled with bombers, layer upon layer of them, stretching from horizon to horizon. Their contrails created an artificial cloud deck that shadowed the ground below. He counted combat boxes and stopped when he reached 20. There were too many to count, too many to engage, too many to matter. He positioned for an attack anyway, not because he believed he could stop them, not because he thought one fighter with 40 rounds of ammunition could make a difference, but because that was what fighter pilots did. They flew, they fought, they continued until they could not continue anymore. He selected a target, a B-17 in the 3rd rank of the lead combat box. He dove from above, accelerating through 8,000 meters altitude, his finger on the trigger, his gun sight tracking the bomber's fuselage. At 600 meters, he opened fire. The cannon hammered. Shell casings ejected from the breech. Tracers arced toward the target. He fired all 40 rounds in a continuous burst. The shells converged on the bomber's right wing, walking across the fuel tank area from wingtip to fuselage. He watched the hits. Counted them. 28 shells struck the wing. More than enough to ignite a fuel tank under normal circumstances. More than enough to destroy any German aircraft. The B-17's wing erupted with explosions. Metal fragments spun away. Large sections of skin were torn open, revealing the internal structure. For 3 seconds, Schroer thought he had finally achieved what all his training and experience had been building toward. A clean kill against impossible odds, a validation that skill still mattered. Then the explosions stopped. The fuel tanks sealed. No flames appeared. The bomber continued flying, its engines maintaining power, its formation position unchanged. 28 explosive hits, 0 effect. The mathematics were final, definitive, unarguable. Schroer pulled out of his dive and turned for home. Around him, the American formation continued toward Berlin. Behind him, dozens of other German fighters were making similar attack runs, achieving similar results: hits without kills, damage without destruction. The self-sealing tanks were doing what they were designed to do: surviving, allowing the mission to continue, enabling the strategic bombing campaign that was grinding Germany's industrial capacity into rubble. He landed with his fuel gauge on empty, the engine coughing as the last drops of fuel burned away. The ground crew chief met him on the runway. "How many?" "None," Schroer said. "I hit one bomber 28 times, center mass, right on the fuel tanks. It kept flying." The crew chief nodded. There was no surprise in his expression, no skepticism. By March 1945, every German pilot and ground crew member understood what they were fighting against. It was not tactics. It was not training. It was industrial capacity deployed at overwhelming scale, protected by technologies that prioritized survival over performance. "There's no more ammunition," the crew chief said. "We fired the last rounds this morning. No replacement stocks are coming." Schroer looked at his aircraft. The Bf 109 sat on the runway, its engine ticking as it cooled, its empty cannon silent. Without ammunition, it was useless. A museum piece, a reminder of what Germany had built when it still believed that quality could overcome quantity. "What do we do?" Schroer asked. The crew chief shrugged. "We wait for the end." 3 weeks later, Werner Schroer surrendered to British forces. The war in Europe ended on May 8, 1945. In the aftermath, Allied intelligence teams examined captured German aircraft and interviewed Luftwaffe personnel. The technical assessments confirmed what combat reports had indicated. German fighters were, in many respects, superior to Allied aircraft in terms of raw performance: faster, more maneuverable, better armed. But they lacked the survivability features that allowed Allied aircraft to operate in sustained combat. No self-sealing fuel tanks, minimal armor protection, single-point failure modes in critical systems. The German aircraft were optimized for the air combat of 1940. They were not designed for the industrial war of attrition that actually occurred from 1943 onward. The American B-17 represented the opposite philosophy. It was not the fastest bomber, not the highest flying, not the most heavily armed. But it could absorb battle damage and continue flying. Its self-sealing fuel tanks could survive dozens of punctures. Its structure could withstand the loss of large sections of wing or fuselage. Its engines could run on contaminated fuel. Its systems were simple enough to be maintained by crews with minimal training. Those characteristics made the B-17 the ideal weapon for strategic bombing. Not because it was perfect, but because it was survivable. And survivability, multiplied across thousands of aircraft and tens of thousands of missions, determined the war's outcome. In 1946, the United States Strategic Bombing Survey published its final report on the European air war. The document analyzed every aspect of the bombing campaign, from tactics to technology to industrial impact. One section focused specifically on aircraft survivability. The statistics were revealing. B-17s equipped with self-sealing fuel tanks had a 38% higher survival rate than early model aircraft without them. That 38% difference meant approximately 1,600 additional bombers returned to base instead of being lost to fuel tank fires. 1,600 bombers represented 16,000 crew members who survived when they might otherwise have died. 1,600 aircraft that flew additional missions instead of being written off as combat losses. The economic impact was equally significant. Each B-17 cost approximately $200,000 to manufacture. 1,600 aircraft represented $320 million in saved production costs. That money was redirected to building additional bombers, training additional crews, and sustaining a strategic bombing campaign that destroyed Germany's ability to wage war. The self-sealing fuel tank, which added approximately $1,200 to each aircraft's cost, returned its investment hundreds of times over through improved survival rates and sustained operational capability. It was not glamorous technology. It did not win headlines. It did not inspire dramatic stories of technological superiority. But it worked. And because it worked, crews came home. And because crews came home, the bombing campaign continued. And because the campaign continued, Germany lost. For Werner Schroer, the post-war years brought opportunities to reflect on his combat experience. He attended aviation conferences where Allied and German pilots gathered to discuss the war. At one such conference in 1952, he met an American B-17 pilot named Robert Morgan, who had flown the famous bomber Memphis Belle through 25 missions over Europe. They talked for hours, comparing experiences, sharing stories that only combat pilots could understand. Morgan described the terror of watching German fighters bore in from head-on, their cannons flashing, knowing that each incoming shell might be the one that penetrated the cockpit or ignited a fuel tank. Schroer described the frustration of scoring hits that should have been lethal, but watching bombers continue flying, their self-sealing tanks doing work that seemed almost magical. "How many times did your fuel tanks get hit?" Schroer asked. Morgan thought for a moment. 12 times that I know of. Maybe more. The ground crews found new holes after every mission. The tanks always sealed. Sometimes we'd land, and the mechanics would show us punctures we didn't even know we had. The rubber just swelled up and closed the holes. Saved our lives probably 6 or 8 times. "We couldn't believe it," Schroer said. "I put almost 300 rounds into one bomber, 47 hits. It should have gone down. I watched the shells explode on the fuel tanks. No fire. Nothing." "Self-sealing tanks," Morgan said. "Best technology we had. Better than the Norden bomb site. Better than the extra guns. Those rubber tanks brought us home." Conversation continued into the evening. Two former enemies, united by their shared experience of aerial combat, discussing the technologies and tactics that had determined their fates. For Schroer, the encounter provided closure. He had not failed as a pilot. He had fought against a system that was designed to survive his best efforts. The self-sealing fuel tank was just one component of that system, but it was a critical component. It transformed the B-17 from a vulnerable bomber into a survivable weapon platform. In 1958, Werner Schroer was invited to tour Boeing's aircraft manufacturing facility in Seattle. The invitation came from Boeing's historical division, which was documenting the B-17's role in World War II. Schroer accepted, curious to see where the bombers he had fought against had been built. The tour began in the engineering archives, where original design documents were preserved. Schroer studied the specifications for the B-17's fuel tank system. The drawings showed every layer of the self-sealing assembly: vulcanized rubber, untreated natural rubber, reinforcing fabric, aluminum outer shell. Each component was dimensioned precisely, with tolerances specified to the thousandth of an inch. But what struck Schroer most was not the engineering precision, it was the production scale. The documents showed that Boeing had manufactured over 6,000 self-sealing fuel tank assemblies per month at peak production. 6,000 per month meant 200 per day, 8 per hour. One complete fuel tank assembly every 7.5 minutes, running 3 shifts, 24 hours per day, 7 days per week. The Germans had understood the engineering. They had analyzed captured tanks. They had developed their own versions. But they could never match that production rate, never sustain that level of industrial output, never maintain the supply chains required to deliver raw materials to the factories, finished assemblies to the aircraft plants. The tour guide, a Boeing engineer who had worked on B-17 production during the war, explained the manufacturing process. We used standardized jigs for every operation. Every tank was identical. Every seam was welded the same way. Every layer of rubber was applied with the same thickness. Quality control was automated. Defect rates were less than 2%. We could train a new worker to handle basic assembly in 3 days. Schroer listened and understood. This was not engineering in the German sense, where craftsmen built individual components to exacting standards. This was industrial engineering, where the process was more important than the individual product, where repeatability mattered more than perfection, where good enough, multiplied by thousands, created overwhelming superiority. "Did you know what these tanks meant to us?" Schroer asked. "Did the workers understand what they were building?" The Boeing engineer nodded. "They knew. We had a poster in the factory showing a B-17 coming home with battle damage. The caption said, 'Your work brings them home.' The workers understood that every tank they built might save 10 lives. That was powerful motivation. They took pride in it. They competed to see which shift could achieve the lowest defect rate. They worked overtime voluntarily. They understood they were part of something bigger than just making parts." That evening, Schroer wrote in his journal, "Today I saw where we lost the war, not in the air over Germany. In a factory in Seattle, where workers who never faced enemy fire won the war by building rubber tanks that refused to burn. I fired 300 rounds at a single bomber and achieved nothing because someone in that factory had installed a layer of rubber that swelled when it contacted fuel. The whole war was decided by such small things, multiplied by millions." The observation was profound. Wars are not decided by dramatic battles or brilliant tactics. They are decided by logistics and industrial capacity, by the ability to produce adequate solutions at overwhelming scale, by the willingness to accept imperfection in pursuit of quantity. The self-sealing fuel tank embodied all those principles. By 1960, the B-17 had been retired from military service. The last operational bombers were sold as surplus or converted to civilian use, but the self-sealing fuel tank technology lived on. Every military aircraft built after World War II incorporated some form of fuel tank protection. The basic design remained unchanged: layers of rubber that swelled on contact with fuel, simple, reliable, effective. Modern self-sealing tanks use advanced materials, synthetic rubbers with better chemical resistance, composite fabrics with higher tensile strength, adhesives that maintain bonds across wider temperature ranges. But the fundamental principle is identical to what was developed in 1941. Use materials that react to fuel by expanding and sealing punctures. No electronics, no moving parts, just chemistry and materials science applied to a life-or-death problem. Werner Schroer lived until 1989. In his final years, he gave occasional interviews to aviation historians studying the air war over Europe. He always returned to the same theme. The war was not won by superior pilots or better tactics. It was won by industrial systems that could outproduce and outlast the enemy. The self-sealing fuel tank was his favorite example. "I was a good pilot," he would say. "I scored hits. I flew aggressively. I understood tactics. But none of that mattered when the bomber I was shooting at had fuel tanks that refused to burn. I could not overcome American industrial capacity with German piloting skill. The equation did not balance. They built faster than we could destroy. They survived longer than we could sustain losses. They won because their rubber tanks worked and our fuel supplies ran out." In 1943, a German engineering report had concluded that self-sealing tanks represented a fundamental shift in aerial warfare philosophy. The report stated, "The Americans have accepted that aircraft will be damaged in combat. Rather than attempting to prevent damage through superior performance, they have designed systems to manage damage and maintain mission capability. This represents a philosophical break from traditional aircraft design. That philosophical break defined the difference between the two air forces. Germany designed aircraft to avoid being hit. America designed aircraft to survive being hit. In the chaos of sustained aerial combat, survival mattered more than avoidance. A fighter that was never hit could only fly as many missions as its fuel supply allowed. A bomber that could survive dozens of hits could fly until its structure failed from accumulated stress or its crew completed their tour of duty. The mathematics favored survival. A B-17 with self-sealing tanks that survived 5 additional missions, delivered 5 times more bombs, gathered 5 times more combat experience for its crew, and contributed 5 times more to the strategic campaign than an unprotected bomber that was lost on its first mission. Multiply that factor across thousands of aircraft, and the advantage became overwhelming. By war's end, B-17s had flown 291,000 combat sorties over Europe. They had dropped 640,000 tons of bombs. They had engaged in thousands of aerial battles, survived millions of rounds of defensive fire, and absorbed battle damage that would have destroyed any previous generation of bomber. The self-sealing fuel tank was one reason they succeeded. Not the only reason, but an important one. In the final analysis, the self-sealing fuel tank represented a lesson that extended far beyond World War II. In any sustained conflict, survival matters more than peak performance. Reliability matters more than sophistication. Adequate technology deployed at scale matters more than superior technology deployed in limited quantities. The side that can accept imperfection and prioritize survival will outlast the side that demands perfection and accepts fragility. Werner Schroer understood that lesson. Robert Morgan understood it from a different perspective. The Boeing workers who built the tanks understood it in their own way. The lesson was simple but profound. In war, as in life, it is not the strongest who survive. It is those who can adapt, endure, and continue functioning when everything else is breaking down. The self-sealing fuel tank did not make B-17s invincible. It made them survivable. And survivability, in the long grinding mathematics of industrial warfare, was the only metric that truly mattered. The German pilot who fired 300 rounds at a single bomber and watched it fly away learned that lesson, the hard way. He learned it in the cold mathematics of combat, where his skill and courage counted for nothing against rubber layers that swelled when they contacted fuel. He learned it in the bitter recognition that his nation's pursuit of engineering perfection had created aircraft that performed brilliantly but died easily. He learned it in the post-war years, when he studied the industrial systems that had defeated him and understood that he never had a chance. The war was won in factories, not in the air. It was won by workers who built rubber tanks, by engineers who designed for survival, by a nation that understood that adequate solutions multiplied by millions would always defeat perfect solutions produced in thousands. The self-sealing fuel tank was not a wonder weapon. It was a practical solution to a real problem, implemented at scale, maintained by standardized procedures, and integrated into an industrial system that could sustain losses and continue operating. 4. 16,000 American aircrew members, whose lives were saved by self-sealing fuel tanks. The technology was miraculous. For the German pilots who watched their best efforts fail against those tanks, it was frustrating and demoralizing. For the historians who studied the war, it was evidence that industrial capacity determined outcomes more reliably than tactical brilliance or technological superiority. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.